We would like to deal today with buckling of plates, but with circular plates. You actually had this case considered before. So this is a radial compression. And the radius equals r. Now, we are introducing also polar coordinates. And polar coordinates naturally are, so this is a center, and distance to the point is, was it in Timoshenko's book R or Rho, if you remember? Let me have a look in your presence. 389, page 389. Yeah, small r. So this is small r, and the angle is theta. But we consider axisymmetric case, in which w is function of only r and not theta. That means that anything that has derivative with respect to theta vanishes identically. So we have then curvatures. And these curvatures are denoted by Greek letter chi. Okay? So there is this chi r in radial direction. That is actually d theta dr. Theta is a negative slope, minus dw dr. That is a notation. So therefore, that is minus d2w dr square. And then there is actually chi theta, actually, that is in the other direction, which equals theta divided by small r, and therefore this is 1 over r dw dr, because theta itself is minus dw dr. Now, we want to write down expressions for the bending moments. Bending moments. So there is mr and m theta. So there is radial moment and circumferential moment. So that if we are taking an element, so there are these moments, that is mr, and this moment, which is m theta. Now mr equals d times, d is a flexural rigidity, d times kappa r plus Poisson's ratio kappa theta. And this equals then d, but kappa r is negative, kappa theta is a negative quantity. Therefore, we are writing that this equals minus d w double prime, that is derivative with respect to r, plus nu r w prime. But w prime is expressed with theta, so first derivative with respect to r is theta, so that that equals D. So maybe it's not a very good notations. Here let us call it phi. And this angle we will call phi. So this one is phi. Okay, so this is m phi, because we denote it by theta, this first derivative. So therefore we cannot use theta again for another purpose. Okay, so as I said, we are dealing with buckling of circular plates, and we have this radial coordinate and circumferential coordinate phi. dd phi here equals 0 because we talk about axisymmetric case. The first the slope is given by minus dw dr, and then we have chi r and chi phi. Okay, so then this equals then theta prime plus nu over rho theta, that is mr. And then m phi equals d kappa, this please take notion that it is phi, kappa phi plus nu, this is chi phi plus nu chi r. Now that equals then minus d 1 over r w prime plus nu w second derivative. Just these two things are exchanged. Okay, whatever is multiplied by nu now will be w double prime, and w prime will be here. So, and this equals just d theta over r plus nu theta prime. Now d is the same as it was for rectangular plates. D is EH cubed 12 1 minus nu square. E is a modulus of elasticity. H is a thickness. Nu is a Poisson's ratio. Okay? Now, we would like to consider the equilibrium of this plate. And equilibrium is actually obtained from considering this element. Okay? So there is this element. So we had this picture already before. Okay, so that is actually this element. So Q is a shear force. So you may want to make this picture again. The only difference is that this is small a, but we denote it as capital R. In the book by Timoshenko, the radius is denoted as small a, whereas we are using notation of capital R. Now we write equilibrium equations. Like in the beams, in the beam, dmz dx equals vy. So that is one equilibrium for the beam. For the plate, it turns out there is much more complex an expression. And this complex expression is like this. I will write it down. mr plus r m phi prime minus m phi plus r Vy or Q, that is this Vy, equals 0. I will give these 2 pages to those who just came so that they could actually share. Maybe you come close and the very beginning pages. Now, what we have actually is as follows. VQ is a shearing force. And if I have axisymmetric distribution, we are actually getting as follows. So we have this element, and here there is this load that is pressing at the boundary. So that is NR. And here there is this Q. Okay, this is a shearing force. So from equilibrium we are getting that this VQ equals actually NR times theta, where this is this slope, because this beam is bending. When it bends, then there is this slope coming out, and when I am actually writing equilibrium equations in vertical direction, then this NR should be multiplied by the slope in order, let us look, this is this vertical position, and that is this NR is like this, and then we need to find its direction in this direction. So we get Q equals NR times theta, or this equals minus NR times W prime, because theta equals minus NR W prime. So we are getting the following differential equation, final differential equation actually. We are talking about homogeneous plates. You actually studied this already. I'm just repeating more or less, and then we will do something more. And that is d del del W, that is Laplace operator, plus NR del W equals 0. So that is a governing differential equation in buckling. This is page 3. Or this equation can be written actually in terms of theta, because W prime minus W prime equals theta. And that is d theta second derivative plus 1 over r, theta first derivative minus theta over r squared plus nr theta equals 0. That is this equation. Now we divide it by d, and we get theta double prime plus 1 over r, theta prime minus theta over r squared, and then plus nr over d. This is not product, that is just an index. And times theta equals 0. So we can call it alpha square. And we get, therefore, theta double prime plus 1 over r theta prime minus theta over r squared plus alpha squared theta equals 0. or that is theta double prime plus 1 over r theta prime plus alpha square minus 1 over r square theta equals 0. Now we can introduce actually a non-dimensional coordinate. U, which is alpha times r. Alpha times r. Then we will have d theta dr equals d theta. R will be, that is d, r equals u over alpha, so that will be alpha here. Therefore, d2 theta dr square equals alpha square d2 theta over du square. So there is alpha square is coming here. So we have, and then we divide by alpha square. So we have u square, okay, d2 theta du square plus u d theta du plus u square minus 1 theta equals 0. So we got this equation, which is naturally Bessel equation. This also is a Bessel equation. Immediately we recognize 1 over r plus something squared minus 1 over r squared. It is a Bessel equation. Therefore, theta equals theta of u equals a1 j1 u plus a2 y1 u. So here, that is Bessel function of the first order and second order respectively. This is first order and second order. Bessel function of first order, Bessel function of the second order. That is why we tried to learn this topic in much detail, because we need it. Now, A1 and A2 are integration constants. Now, we also said that we consider axisymmetric case. That means that if this is a plate, then so that is the buckling displacement. That means that first derivative equals 0. dw dr at when r equals 0 must be 0, otherwise it is not axisymmetric. So that means that theta at 0 equals 0. But y1 of u takes infinite value at 0. Okay, u, if you remember, is alpha r. So when r goes to 0, u goes to 0 naturally. Therefore, we should put a2 must equal 0. Now, so let us say theta of u then equals a1 Bessel function 1 of u. And if you remember, Mr. Andres showed us immediately in the first lecture that j1 at 0 equals 0. So this condition of axial symmetry is satisfied by the first term. And second term, therefore, must be dropped. If you remember here the figure, Bessel function of the first kind zeroth order is non-zero, but the rest of them is 0. there was a figure also, a proper figure, that only the zeroth order function is not 0. The rest in the beginning is 0. Now we should consider the boundary conditions. Now, if this is clamped, if when R equals R, plate is clamped, that means that dW dr equals 0. Naturally, also W equals 0. So theta equals 0. Therefore, we get that J1 of alpha R must equal 0. That is a transcendental equation. If you remember, Mr. Endres also gave us tables of Bessel functions, of J0 and J1, etc. And in these tables, we can search where is this root, at which point of argument this J1 equals 0. It turns out that this alpha R is approximately 3.832. But we denoted that alpha square equals NR over D. So therefore, we substitute here alpha equals here this, so 3.832 divided by R square equals NR over D. Okay? So from here we get NR. NR is 3.832, that is approximate because it is an approximate root, squared, yes, D over R squared. And that equals 14,682 D over R squared. Okay? So as we see, for uniform case, uniform and homogeneous plate, for uniform and homogeneous plate, the mode shape is given by the Bessel function, okay, mode shape. How much, what is this mode shape? Let us look. Theta of R equals A1 J1 of U. That is A1, excuse me, A1 J1 alpha R. But alpha is A1 J1. How much is alpha from here? Alpha equals 3832 divided by R. 3.832 R and small r. So it is a mode shape. Mode shape of the slope is Bessel function 3, let me write here, Bessel function 3832 R over R. It's beautiful that it's naturally non-dimensional coordinate. Small r divided by capital R. That is a mode shape. So, Bessel, okay, mode shape is given as a transcendental function because that is an infinite series. This function is a transcendental function. For evaluating at any point, you should have an infinite series. We can actually reduce number of terms, say by 100 terms, 200 terms, etc., depending on our wish. However, this this is a transcendental function, and we got it. Now let us consider what happens. So that was clamped. Clamped at the end. 7. Yeah, this formula, first of all, before we go, was given by Brian, an English in his paper Proceedings of the London Mathematical Society, volume 22, pages 54-67, in 1891. So it was long ago, much before any of us in this room was born. Much, much before. Now, what happens if this here, it is simply supported. So simply support, okay, first of all, clamped, we are denoting like this. That is clamped. Now, simply supported, we denote by another line, concentric line here. This is actually a Russian notation. This is concentric line. Very close by. So that is simply supported. So here we obtained already. Now here we have a question mark. And naturally we have this NR, yes, everywhere. So it is actually uniformly loaded around the circumference. Uniform compression around the circumference. Now we want to find what happens with simply supported case. In simply supported case, naturally boundary condition will be MR equals 0. When R equals capital R. Now that means actually when we found already MR. MR is D theta prime plus nu over R theta. So when R equals capital R, this must be 0. So then we substitute for theta an expression A1 J1 alpha R. That is our general expression of the mode shape, and we get the following equation: alpha R J0 alpha R plus minus 1 minus nu J1 alpha R. Because derivative of, here is derivative of J1 is proportional to J0 and J1. So therefore, we get this. And this equals 0. Now we have to solve this equation. Now, this is a transcendental equation. Has infinite roots. Now roots depend upon nu, Poisson's ratio, because there is nu here. If they depend upon Poisson's ratio, we should specify the nu. So if nu equals, say, 1/3, then the minimum root alpha R, minimum root, equals approximately 2069. We substitute this, and okay, from here we get what is alpha. Alpha was square root nr over d. R equals 2069. From here we get nr. And then equals 2069 squared, which is 4282d over r squared. Do you have a calculator, anyone? Okay. So what we got actually, nr equals 14682 d over r squared. That is clamped. And nr equals approximately 4282 d over r squared. That is simply supported. So how many times bigger? No one has a calculator? Okay, so it's about 3.5 times bigger, and not 4 times. In order to be 4 times, we had to have more than 16. So in the beam case, if you remember, in the column case, P simply supported equals pi square EI over L square. P clamped equals 4 pi square EI over L square. So there was a factor of 4 for the column. Here for the plate, we don't have exact number, not an integer number, excuse me, but number that is not very far from that, approximately 3.5 times more. Clamped column, clamped plate naturally should be stronger. It should buckle at greater value of the load. Now we will deal with some unusual closed form solutions. Now, what is unusual? In 1981, Professor Conway of Cornell University, he published a paper that is called approximately Unusual Closed Form Solutions for Bending of Circular Plates. Okay? He called it unusual. Why it is unusual? What did he do? So he took a circular plate on some, I think, elastic foundation. Those who took vibration course will recognize that elastic foundation is always bringing some interesting features. But in this particular case, we are not talking about an interesting feature, but he considered h of r, so that means that thickness is variable. And it is, I think, proportional to r cubed. If thickness is variable, that means that what is this thickness is variable? So the plate is like this. Okay, when you go, thickness becomes bigger and bigger. Actually, it's not straight. I mean, like something like that. Okay. So such a plate is on the elastic foundation. Okay. Professor Conway found unexpectedly a simple polynomial solution. So therefore, he called his solution unusual. Why did he call it unusual? He says, for uniform plates, I have Bessel functions. For non-uniform plates, I have simple polynomials. That is what he maintains. So we would like to follow can we follow the footsteps of this most interesting result? It is most interesting because, look, thickness is varying, and suddenly you are finding closed form solutions that you would never expect this. For example, if thickness is varying, naturally you would search for finite element solution of the problem, is it right? Or finite difference solution of the problem. Now, Professor Conway was able to obtain very simple closed form solution. This most unfortunately happens for this one specific variation of this flexural rigidity or thickness. So we would like to ask, can we get something like that in backlink? That is a question that we would like to pose. And so is there a similar result in backlink of plates? That is a question. The answer is yes. The answer is yes. First, I would give you, without derivation, so what we want actually is, imagine that E is a function of R. If E is in function of R, we will have another differential equation. Look, the same was in beam case. Let's say column. Let us say column. If it is uniform, then we have EI we denote as D. So D, W first derivative, plus PW second derivative equals 0. That is uniform. If E is a function of X, we have dW second derivative plus PW second derivative equals 0. So these are different equations. Just from here we can easily obtain, if D is taken out, if it is constant, then we get this. Okay? Say okay. Say yes. So differential equation is this. D theta double prime plus 1 over R theta prime minus theta R square plus D prime theta prime plus nu over R theta plus NR theta equals 0. So it's much more monstrous expression. So please, if this is 0, then we get previous equations that we had. If D prime, this is D capital D dr equals 0, we have uniform case. Now we would like to, now my question is as follows. Assume, now we are solving semi-inverse problem. We postulate W. This leads to postulate of theta, which is minus dW dr. For example, this W equals some A times R square minus small r square squared. Now that is for clamped case. Why? Because what we should have actually is as follows. Look, W at R must equal 0. And dW dr at R equals R must equal 0. These are two conditions. These conditions are satisfied. If I substitute capital R instead of small r, I get 0. If I differentiate this, then I'm getting 2 times r squared minus small r squared, and then 2r, and then it is also 0. So this satisfies the boundary conditions. Now I have, imagine that I have just nothing to do in the world, and I'm asking the following question. Is it possible that W equals A times R squared minus R squared squared is an exact mode shape? Yeah, by the way, Professor Conway did not solve a semi-inverse problem. He just guessed. He just said, if h of r is a cubic function, I have unbelievable, unusual, surprising, stunning result. That was what his result was. He did not, so to say, tell us where did he get this? Where did he get this cubic term, so to say? Here we are doing differencing. We are saying, I would like ahead of time to have this W equals R squared minus R squared to be a mode shape. We are as if, so this is a plate, and we are telling this plate, okay, we say we are standing here, say student who takes this course and tells, I want you to have this expression as a buckling mode. Okay? That is what is actually happening. Okay, we can check if that is possible or not. Now, because this W equals A times R squared minus small r squared squared, theta, of course, is a derivative of this. And theta is, this is a fourth order polynomial, so theta is a third order polynomial. Third order polynomial. Now let us look here. Here at this. This is a third order polynomial, theta. So this expression is a third order. This is a third order polynomial, but there are second derivative here. So that is a first order polynomial. So D must be a second order polynomial. Okay? D must be a second order polynomial. So we substitute this D equals D0 plus D1R plus D2R squared. We substitute this in the differential equation. Okay, so that is, now I want to find D0, D1, and D2. We substitute there, and we get the following equation. Okay, substitution is like this. d1r square 1 plus nu minus 8d0 minus r square nr plus 2d2 1 plus nu r minus d1 11 plus nu r square minus nr plus 2d2 7 plus nu r cubed equals 0. Okay, from here we see that, look please, d1 must be 0 because there is nothing here, and this is a constant term. Okay, this is r in zeroth power, this is r in first power, r in square, and r cubed. So this d1 must be 0, so this term is vanishing. And it turns out that d2 equals d0. d2 equals minus d0. Excuse me. So we get actually d equals d0 1 minus 2r square 3r square. Okay, then nr equals, nr critical, equals 4d0, 7 plus nu, divided by 3r square. Okay? That is the first closed form solution obtained ever for circular inhomogeneous plate buckling. If you remember, Brian did not obtain closed form solution. He obtained transcendental equations that should be solved, etc., etc. I could have said since 1891, but that will be not correct, because also in 1891 he did not obtain the closed form solution. Therefore, we can borrow Conway's terminology and call this solution to be unusual. Okay? Actually, collection of such solutions is reported in a book, Unusual Closed Form Solutions for Eigenvalue Problems of inhomogeneous structures by me, and it will appear next year. I just borrowed this word unusual. Also, I felt a bit uncomfortable to have in the title unusual, but then I am explaining that we are borrowing the terminology of Professor Conway. And I asked actually Professor Conway to write a foreword to the book And he kindly agreed. I never met him, actually. So there is a foreword written by Professor Conway where he explains unusual and other things. Now we would like to go to the simply supported plate. But before that, maybe we will say, maybe before that, forget this. Now, nu equals, first of all, the difference a bit. Let us talk about the difference with uniform solution. Uniform case, NR is not a function of nu. It's not a function of Poisson ratio, if you remember. It was 14 something d divided by r squared. In non-homogeneous, NR is a function of nu. So if nu equals 1/3, then we get NR equals 4d0, 7 plus nu, 3r squared. And if it is 1/3, it becomes 9, 7, 7, 8, d0 over r squared. That is what we obtained. Now we would like to ask the following question. I think it is a very interesting question. E is a function of r here. We can calculate some average E or effective E or effective D. The average we can calculate as follows. Look, 1 over pi r squared, and then integral between 0 to pi, from 0 to r, d of r, r dr d theta. That is this dA. This is an element of the area. And now we can, so if I substitute this expression here, I get d average equals 1 over pi r squared, this integral, d0, 1 minus 2r squared, 3r squared, r dr d theta, from 0 to 2 pi, from 0 to r. So that is what? That is plate average. I'm integrating d around the plate's surface and divide by the area. Okay? For example, if you have inhomogeneous pizza, you can ask the question, what would be the thickness of the uniform pizza that has the same weight, for example? Is it right? Pizza is also a circular plate. So we get this, the average equals, I think, 2/3. 2/3 d0. Now, we know the formula by Bryan. Bryan's formula for uniform case is NR, that corresponds to D average, that equals what? 14,682, is it right? And then D square. So D square will be here, I substitute 2/3 D0 divided by R square. So this comes approximately 9,788 d0 r square. So we had non-homogeneous had an NR equals 9778 D0 R square. Average has 9788 D0 R square. Okay, the difference is 1.04%. So this average behavior, how to interpret this result? This result is interpretable like this. I have D. You gave me any D. The first approximation that the engineer could do, you know what? You can say D is a variable function of R. I don't know how to solve the problem. I need maybe to solve by finite element method. But if you, my boss, or if you, my colleague who wants my help, I can immediately calculate for you something approximate immediately. You give me any variation of D, I will average it over the plate surface, and I will get, by this means, some average plate, uniform plate. For that plate, we can use Bryan's formula. And Bryan's formula will give us some result for that averaged plate. And hopefully that plate is not very far in its behavior than this variable plate. You may want to write it down. In this particular case, in your words, in this particular case, difference was 1.04%, which is an extremely good approximation that I personally did not anticipate. I would think that there will be 5 to 20% difference, but I don't say fortunately, because it's not. I mean, surprisingly, that is a very good approximation. It turns out it's just 1%. Any questions up to this point? No. Then we can, this is page 16. Page 17. Homework assignment. Please come up with your own approximate function, approximating polynomial that satisfies the boundary conditions. So I used, if you remember, R square minus R square square, W equals A. That is what I used. So not this, naturally, but something else that satisfies conditions at R equals R, W equals 0, and dW dr equals 0. Okay, that is dW dr. And find D of R, as well as find the N critical. Now that we can solve this problem, you can obtain, and I would like each of you to do a different thing. Why? Because then we can compare. Now, what will happen is as follows. You will try one function, and it satisfies the boundary conditions. But it may happen that that function does not lead to any D, or it could lead to a negative D. You see, here we have something that is very fortunate. As a result of this method, D of R is a positive function. If by chance D of R would turn out to be a negative valued function, then we would say that solution does not exist because that is a physically unrealizable problem. We would say that operation succeeded, but patient died. Okay? That would be not interesting a case. So here, operation succeeds and patient is alive. Well and feels very well. So you will find one function and there is no solution. Then you go to another function. Okay? If you have any questions about functions acceptability, you can email me and ask, is this function acceptable? Naturally, you can check by yourselves immediately, because what happens is as follows. This function should satisfy conditions, like at axial symmetry, radial symmetry. Okay? What is radial symmetry? That means that here, at r equals 0, w equals some constant. Okay? Then it decreases. But main thing is boundary conditions. So w at r equals w at small r equals capital R equals 0, and first derivative equals 0. You can build many functions like this, each of you. Okay? It's bad. I recommend not to cooperate with each other on that. Because when you cooperate, then you are entering into the mindset of the other person. Sometimes it is good to cooperate, sometimes not. Why? Because we would like to get different solutions. And next time, when you bring me the homework, I would like to ask you that the first page be just expression for d of r, w, okay, I will write down here. So it will be clamped plate. Then w of r, then d of r, n of r. Okay? Then you also please do calculations d average and compare n that corresponds to d equals d average and percentage-wise difference between this and between uniform case. Just one homework for next time. Any questions? If you have no questions, then we will go to another material. Actually, this material is covered in these lecture notes that we have. And that will be by the way, do you have any questions about these probabilistic solutions that we had past time? You remember we talked about imperfections. Maybe we will talk a bit more about imperfections, and I will cover the new material next time. So what happens is as follows. Euler, in 1744, dealt with columns. And he derived his famous formula, P critical equals pi square EI over, actually, he wrote 4L square, but the length is 2L. Okay? And here he actually had, he had support, and here he had this, like force was like this. Okay, some force, concentrated force. So it looks like clamped free in his picture. Okay, it looks like this. That is his picture. So this looks like clamped free. And this formula also looks like clamped free. Okay? So therefore many authors say that Euler never considered simply supported case, they say. He considered clamped free case. But they don't pay attention that he says that length is 2L. And then boundary conditions are of simply supported. So this is actually simply supported case. Okay? Because that's 2L. Now, I think D'Alembert wrote an encyclopedia in 1783, when Euler still was alive. However, he did not include Euler's formula. He saw that is an unimportant result. Because indeed the structures were not slender. They were not long enough in order buckling to be a consideration. Therefore, I mean, D'Alembert saw that it's just mathematical exercise, so to say. However, even before Euler, I think 1642, Galilei wrote his famous book, discussion about two new sciences. In English, they don't translate discourses; they just say two new sciences, in which he actually uncovered dynamics and strengths of materials. Okay? Just very, very small thing we could say is that Galileo Galilei's, I would say, I don't know how to call it exactly, whether it was tolerance or unbelievable cleverness or desire to live or understanding that live person can accomplish more than dead person. So he actually recounted his teachings about, about Earth rotating around the sun or the opposite. So when he was demanded, so he decided publicly to recount and say that he was wrong. As a result, he stayed alive. So he was sent to the home imprisonment. Okay, it reminds us of dictatorial regimes, but in dictatorial regimes people are killed, so he at least was just in home imprisonment. However, his revenge, some people say, but even more, because he was alive, he was able to write this most famous book about, in which he actually founded two sciences, two new sciences, dynamics and strengths of materials. Now, in his book, he actually wrote it as a conversation. And conversation is between three people. And we do not want now to... Some people say that Galileo, in one of the person whose name is Simpleton or Simplicio, he as if thinks that these are his enemies, and he is therefore calls them simplistic. However, other people say that no, that is not correct. That Galileo actually talks about himself when he was very young. So he was simpleton, then he became more wise, and now Salgiati is talking on his behalf. So there it says, look please, Galileo says much before Euler that one cannot construct huge buildings I mean, that is approximate, yeah? Huge buildings, and, for example, trees cannot grow to huge heights because under their own weight, the system may, he did not say buckle, system may lose equilibrium under slightest disturbance. It sounds very much like, do you remember we talked about disturbances and responses, small disturbances? Do you remember Lyapunov's definition, 1892? So it sounds like that, but at least that is a conversation between these three colleagues or three friends or three enemies, I don't know. But most recently I read that this is actually Galileo talks to himself. I mean, but at various stages of his life. That is a very beautiful, I think, explanation rather than, you know, he would ascribe something to his enemies because maybe these enemies even don't know what he's talking about. So that is it. And interestingly, in 1891, Greenhill in England, Proceedings of Royal Society of London, he published actually a paper which is just one sentence and I'm done. Paper that is called The Height That Trees Can Grow. Okay? And so he has Bessel functions there. And interestingly, there is an article that I have, I hope I will find, the height the man can grow. They do not, by the way, almost approximately the same. That is Harvard University. I think 1991, something like that. It considers what is a maximum height, person can grow. So that if someone is not very tall, we can say that at least he can buckle with less possibility. Thank you very much.